We present MapPrior, a generative approach for bird's-eye view map layout estimation. The goal of BEV map layout estimation is to estimate a scene layout given a self-driving car sensory input. This task is important because the layout can be used for downstream mapping or driving planning tasks. A successful BEV model should ideally have three properties. First, the prediction to accurately match the true layout. Next, the generated layout should also be realistic and in distribution. And finally, the model should be calibrated and have an accurately quantified uncertainty. Previous state-of-the-art works typically used a predictive model to produce a layout. Given a single input, a single prediction is generated. The generated prediction is decently accurate. However, the layout has obvious artifacts and is out of distribution. For example, here the lane markings are jagged and have visible gaps. This can hurt downstream tasks. Finally, state-of-the-art predictive models often have poor calibrations. We propose to address these challenges by combining BEV perception with generative modeling. Perception models provide excellent accuracy, while generative modeling can provide realistic, in-distribution outputs that are uncertainty-aware. These yield us the best of both worlds. We propose MapPrior, a novel BEV perception method that is more accurate, realistic, and uncertainty-aware, by using a combination of a predictive model and a learned deep generated prior. MapPrior is composed of two stages, namely predictive stage and the generative stage. During the predictive stage, we adopt a standard discriminative BEV perception model, which projects sensory input into bird's eye view and uses a segmentation head to estimate the layout. In generative stage, we first use a vector quantized autoencoder to learn a prior distribution of the ground truth map. This regularizes the output space, causing all reconstructions to be realistic. Finally, we perform sampling in a discrete latent space using a transformer conditioned on the initial estimation from the predictive stage. We show our model beats baselines both quantitatively and qualitatively. Our quantitative results show that MapPrior significantly outperforms previous state-of-the-art approaches for BEV perception in accuracy as shown by the LU scores, realism as shown by the MMD, and uncertainty awareness, which is quantified by expected calibration error. In a qualitative comparison, discriminative BEV perception baselines produce results with clear artifacts. For example, lane markings are discontinuous, and roads and pedestrian walkways also have unrealistic gaps. In contrast, our model produces semantic map layouts that are clean, realistic, and in distribution. Because we are using a generative approach, we can generate multiple potential map layouts for a single input. By combining the generated samples, we can determine the model's uncertainty map by estimating their variance. We show that MapPrior's method of estimating uncertainty significantly outperforms state-of-the-art methods. MapPrior's uncertainty more closely matches the error map compared to the baselines. However, since MapPrior uses autoregressive sampling and produces multiple samples per input, its inference speed is limited. To address this, MapPrior one-step predicts a single sample per input and generates all tokens simultaneously, resulting in a worse uncertainty awareness and marginally worse MMD score. However, one-step MapPrior achieves almost the same IOU score and runs around 8 times faster than the standard version. In addition, by replacing the condition with noise, MapPrior is able to generate a realistic, infinitely long road with progressive sampling. In summary, MapPrior improves BEV perception accuracy, realism, and uncertainty awareness by using a generative approach for predictions.